Hello all. In this lecture, we will continue the discussion about the problems of uh, congruences. So first of all, we start with the theorem. If A congruent to B mod M, then A raised to n congruent to B raised to n modulo M for any positive integer n. Proof. The proof is by contradiction method. We have when n is equal to 1, it is clear that the statement is true. That is, the statement is true. Statement is clearly true if n equal to 1. Now, by the principle of mathematical induction, weak induction, um, actually the proof is we are doing by induction method. So the statement for n equal to 1, the statement is true, and we assume that it is true for an arbitrary positive integer k, that is a raised to k is congruent to b raised to k modulo m if a congruent to b modulo m. Then by theorem 4.1, in theorem 4.1 we have proved that if a congruent to b modulo m, c congruent to d modulo m, then their product AC is congruent to BD modulo M. Therefore, A raised to A into A raised to K congruent to B into B raised to K modulo M. That is, we have A raised to K plus 1 congruent to B raised to K plus 1 modulo M. So if we assumed that the result is true or the statement is true for n equal to k, we have proved that therefore the result is true for n equal to k plus 1. Then the principle of mathematical induction, the result is true for every positive integer n. For all positive integer n, that is n belongs to z plus. So again now we moving to the problems. First problem, prove that there is no integer of the form 8n plus 7 can be expressed as a sum of squares of is sum of three squares. Is sum of three squares. That means we need to prove that there is no integer of the form 8, 10 plus 7 which can be expressed as a sum of three squares, sum of the squares of three integers. The proof is by, we prove this result by contradiction method. So assume that by contradiction, assume that there is an integer, there is an integer capital N of the form 8n plus 7 that can be expressed as the sum of three squares. So we have, that is n is equal to, n is a number of the form 8n plus 7 such that x square plus y square plus z square for some integers, for three integers x and y, x, y and z. Now we know that it is we assumed that it can be expressed as a sum of three squares and it is of the form 8, 10 plus 7. That means we can say that n is congruent to 7 modulo 8. So that is we have to we have the result x square plus y square plus z square congruent to 7 modulo 8. Now we need to prove that this makes some contradiction. So we know that x is x, y and z are integers. Then also we know that when x, y or z any integer is divided by m or 8, here it is 8, the divisor is 8. So divided by 8, then that integer must be congruent to the remainder obtained, and any integer is congruent to its least residues, one of the least residues. So x must be congruent to, therefore, we have x must be x, y or z and z. X must be congruent modulo 8 to the least residues, one of the least residues 0, 1, 2, 3, 4, 5, 6 or 7. 6 or 7. Now by the above theorem we can have, when x is congruent to some a modulo m, then x raised to n is congruent to a raised to n modulo m. So since x is congruent to at least one of these residues, then x square must be congruent modulo 8, must be congruent modulo 8 to 0 square, 1 square, 2 square, 3 square, 4 square, 5 square, 6 square or 7 square. That is x square is congruent modulo m to 0, 1, 2 square is 4. Now 3 square is 9. 9 is again 1. Now 4 square is 16. 16 is 0. Then 5 square. 5 is, we can reduce the number 5 under modulo 8 as 5 is congruent to minus 3 modulo 8. So instead of 5 we can use what? Minus 3. So minus 3. 9. 3 square is 9. 9 is congruent to minus 3. So minus 3 square. Minus 3 square is 9. 9 for 9 we have again have 1. Now 6 square. 6 square is 36. 36 is again 4. Then 7 square is 40. 7 square is 7 is congruent to minus 1 modulo 8. So 7 square is congruent to 1 modulo 8. So the square of x is congruent modulo m to one of the numbers 1, 0, 1 or 4. Therefore, so we have for any integers, that is we have x square is congruent to 0, 1 or 4 modulo 8, and y square similarly 0, 1 or 4 modulo 8, and we have z square also congruent to 0, 1 or 4 modulo 8. Then x square plus y square plus z square must be congruent modulo 8, must be congruent modulo 8 to exactly one of the sums. Zero plus 1 plus 0 etc. up to 4 plus 4 plus 4, and we can see that of these none of them is congruent to 7 modulo 8, but of these none of them is congruent to 7 modulo 8, which is a contradiction. Hence it is proved. Okay. So there is no integer n of the form 8n plus 1 which can be written as the square of sum of squares. Now we can move to the next problem. Find the remainder when 16 raised to 53 is divided by 7. Sorry, divided by 7. So we have to find the remainder when 16 raised to 53 is divided by 7. The power is a very large number, and hence this will be very large number. So it is very difficult to find the remainder by the actual method. So we can make use of the congruence relations here. First of all, we have to find the congruent number when 16 is divided by 7. We know that 16 is congruent to 2 modulo 7. And in this lecture, first we have proved that if a raised to a congruent to b modulo m, then a raised to n is congruent to b raised to n modulo m. So using this relation, we can see that 16 raised to, therefore by that theorem, 16 raised to 53 is congruent to 2 raised to 53 modulo 7. Now we need to look upon 2 raised to 53. Actually, we have to find a smallest power of 2, for which it is congruent modulo 7 to a number which is less than 7. Or if we get a number like if we get a power of 2, for which 2 raised to that power is congruent to some 1 modulo 7, then it will be very easier to find the next remaining powers. Okay. So obviously we have 2 is congruent to 2 modulo 7, but 2 cube is, we know it is 8, so 8 is congruent to 1 modulo 7. So 2 cube is congruent to 1 modulo 7. But we have to find what 2 raised to 53. So 2 raised to 53 is 2 raised to 3 into so 2 raised to 53 can be written as 2 raised to 3 into 17 plus 2. And we know that 2 raised to 3 is congruent to 1 modulo 17. So 2 raised to 3 into 17 is congruent to, or this is equal to, not congruent to, this is again equal to what 2 raised to 3 raised to 17 into 2 square. So this is congruent to 2 raised to 3 is congruent to 1 modulo 17 into 4 modulo 7, not 17. So this is congruent to 4 modulo 7, 2 raised to 53. That is by transitivity property, we have 16 raised to 53 is congruent to 2 raised to 53, which is congruent to 4 modulo 7. So we have 16 raised to 53 is congruent to 4 modulo 7. That is 4 is the remainder obtained when 16 raised to 53 is divided by 7. Okay, so we can move to the next problem. Find the remainder when 3 raised to 247 is divided by 17. So first of all, we have to find a power of 3 which is congruent modulo 17 to smallest number which is less than 17. We have 3 square, 3 is congruent to 3 modulo 17. 3 cubed is congruent to 27. 27 modulo 17. 27 is actually congruent to 10 modulo 17. And we have 3 raised to 3 is congruent to 10 modulo 17. Our aim is to find a power of 3 which is congruent to some smaller number like 1, 2 or 3 like that. So it will be better easy to take the powers. So 3 raised to 3 is congruent to 10 modulo 17. 3 raised to 4 is congruent to 10 into 3 30. 30 actually 34 is a multiple of 17. So it is congruent to minus 4 modulo 17. 3 raised to 4. And we know see 4 into 4 is 16. 16 is congruent to minus 1 modulo 17. So we can use that result. So 3 raised to 4 square is congruent to minus 4 square modulo 17 using the above theorem. So 3 raised to 4 square means 3 raised to 8 is congruent to 16. 16 is congruent minus 1 modulo 17. Now again squaring we have 3 raised to 16 is congruent to 1 modulo 17. But we have to find 3 raised to 247. But by division algorithm 247 is equal to 16 into 247 is equal to 16 into 15 plus 7. So we have 3 raised to 247 is congruent to 3 raised to 16 raised to 15 into 3 raised to 7. This is not congruent. This is equal to this is congruent to 3 raised to 16 is congruent to what? 3 raised to 16 congruent to 1 modulo 17. So 3 raised to 16 raised to 5 is congruent to 1 raised to 15, that is again 1. So congruent to 1 into 3 raised to 7 modulo 17. So 3 raised to 7 modulo 17. Actually we have 3 raised to 4 is congruent to minus 4. So 3 raised to 7 is 3 raised to 4 into 3 cubed. 3 cubed is congruent to what? 3 cubed is congruent to 10. And 3 raised to 4 is congruent to minus 4. 3 raised to 7 we can write it as 3 raised to 4 into 3 cubed. 3 cubed is 10. 3 raised to 4 is minus 4. So 3 raised to 7 can be written as 3 raised to 4 into 3 raised to 3 modulo 17. So 3 raised to 4 is congruent to minus 4. 3 cubed is congruent to 10 modulo 17. So it is minus 40. Minus 40 is congruent to minus 40 is congruent to we know that minus 40 minus 34 is multiple of 17. So the next multiple is 30. After 34 the next is multiply 17 into 3, that is 51. So for that here we can write minus 40 is congruent to 6 modulo I'm sorry, minus 6 modulo 17. Modulo 17 or 11 modulo 17. 3 raised to 247 is congruent to 11 modulo 17. Now please do the problem as exercise. Find the remainder when 3 raised to 181 is divided by 17. Okay, let's stop here. Thank you. Thank you all.